Hey everyone, and welcome. Today, we are going to break down merge sort. It's this super elegant and powerful sorting algorithm that you find working behind the scenes in all sorts of places, from sorting massive databases to helping the internet run smoothly. So if you've ever wondered, how do you sort millions of things really fast? Well, you're about to find out.
So here's what we're going to cover. First, we'll get into the core strategy, this beautiful idea called divide and conquer. Then we'll look at the two main phases, the split and then the merge. After that, we'll walk through a complete example, step by step, to see how it all fits together. And finally, we'll dig into why this thing is just so darn efficient.
Okay, let's start with the big picture. The whole philosophy behind merge sort is this principle called divide and conquer. And honestly, it's such a fundamental strategy for problem solving, you probably use it all the time and don't even think about it.
Right. Think about it. If I handed you a 10,000-piece jigsaw puzzle, you wouldn't just stare at the whole pile and hope for the best, would you? No way. You'd probably find all the edge pieces first, then maybe group the rest by color, and solve little sections one at a time. That's it. That's divide and conquer.
And this is exactly what merge sort does with a list of numbers. It takes this big, jumbled problem and just keeps breaking it down and down and down until the problems are so tiny that they're laughably easy to solve. And then it cleverly builds the solution back up. It all boils down to these three simple steps. 1, you divide the list. Just chop it in half. 2, you conquer by sorting each of those halves. And 3, you combine them by merging the two sorted halves back into a single sorted list. Divide, conquer, combine. We're going to see this pattern over and over.
Okay, let's zoom in on phase 1, the recursive split. This is the divide part of our strategy. Now that word recursive can sometimes sound a little scary, but all it really means is that we're going to apply the exact same logic, the split, over and over again to smaller and smaller chunks.
So, here's our starting point, a totally unsorted list of 8 numbers. It's a bit of a mess, right? Our job is to get these in order, from smallest to largest, and we're going to use our new strategy to do it.
First move, super simple. Find the middle and split the list into 2 smaller lists. We haven't actually sorted anything yet, but we've already taken that one big problem and turned it into 2 smaller, less intimidating problems.
But why would we stop there? This is where the whole recursive idea comes in. We do the exact same thing to the 2 lists we just made. We split them in half again. So now we've got 4 little lists, each with just 2 numbers.
And you guessed it, we do it one more time. We keep splitting and splitting until we physically can't split anymore. We're left with the absolute simplest problem you can imagine. 8 separate lists, and each one has only a single number in it.
And this right here, this is the light bulb moment. A list with just one item in it is, by definition, already sorted. I mean, what else could you do with it? This is our base case for the recursion. The divide part of our job is officially done. We've broken the problem down to its simplest possible form. Okay, so we've torn everything apart into these tiny, sorted lists. Now for the really cool part, phase 2, the merging magic. This is where we start to build things back up, but in a very smart, very organized way. This merge step is the heart and soul of the entire algorithm. The key is that it takes 2 lists that are already sorted on their own, and it combines them into a new, bigger list that is also sorted. Look how it just perfectly weaves together 3, 9, and 5, 7. This little operation is the real workhorse here. So how does it actually do that? Well, it's just a simple comparison game. You look at the very first number in each list. Which one's smaller? You take that one and put it in your new result list. Then you just repeat that, always comparing the numbers at the front of the line. You keep doing that until one of the lists is empty, and then you just tack on whatever's left from the other list. It's so simple, but so effective.
All right, theory's great, but I think it's time to see this thing in action from start to finish. Let's trace our original list of numbers through this whole process, from the chaotic mess it started as to the final, beautiful, sorted list.
The best way to picture this is to think of it like a tree. The algorithm starts at the top with the full list and splits its way down the branches all the way to the leaves, which are single-element lists. Then it starts climbing its way back up the tree, merging pairs together at each level until we get all the way back to the top with our final, single, sorted list.
And after that very last merge, right at the top of the tree, this is what we're left with, a single, perfectly sorted list. We took that jumbled mess and brought it to pristine order. It's kind of beautiful, right?
So now we know how it works, but the really big question is, why do people use this? What makes it so good? Let's get into the analysis of its speed, because that's really what makes merge sort a go-to for dealing with huge amounts of data.
Now this is where it gets really, really cool. Think about how much work we do at each level of merging. At the very bottom, when we're merging all those single elements, we have to look at all 8 elements to pair them up. Okay. At the next level up, we're merging bigger lists, but again, we process all 8 elements. And at the very top, that final merge, we're still processing all 8 elements. Get this, at every single level, the total amount of work is the same. It's always proportional to n, the number of things we're sorting.
So we can break down its total speed into 2 parts. First, how many levels are there in our tree? Well, since we keep having the list, the number of levels is what we call the logarithm of n, or log n. With 8 items, we had to split it 3 times to get down to 1. Well, log base 2 of 8 is 3. It checks out. The second part is the work we do on each level, which, as we just saw, is n.
Now, for all you math fans out there, there's a really formal way to write this down, called a recurrence relation. It looks complicated, but all it's saying is that the total time to sort n things is just 2 times the time it takes to sort half that many things, plus the time it takes to do that n-sized merge at the end. It's a perfect mathematical description of the algorithm.
And when you put those 2 pieces together, the n amount of work we do across the log n number of levels, you get this, a time complexity of O(n) log n. This is what makes it a champion. A more basic sorting algorithm might be O(n) squared. For 1,000,000 items, n log n is thousands of times faster. That consistency is why it's such a beast for big jobs.
So we've seen just how fast and reliable merge sort is. But in the world of computer science, there's pretty much no such thing as a free lunch. There's always a trade-off. Which leads to one last question. To get all that amazing speed, what's the cost in terms of memory? That's a great question to chew on and a super important one when you're building real-world software.